I'm really excited to be back at RailsConf. This is my first conference since 2019. Dang, it is nice. Did you all miss this? Yeah. So my name is Brad Urani. I'm a principal engineer at Procore. I live in Austin, Texas. What the hell is that? Oh, there we go. Procore builds software for the construction industry. If you're building a skyscraper like this one, a shopping mall, a subway system, you're probably using Procore. It's a big suite of enterprise software. We build the software that builds the world. That is our motto. Holy cow. There's one of our iPad apps used for building design and things like that. We are, I think, 200, maybe 300 Rails developers strong. Grew from a tiny little shop up into a great big one, starting on Rails 0.9 over 16 years ago. We now have, I think, might be the world's largest Rails app. I know that Shopify's got a big one. Not sure if you all are still contributing to that or if it's still growing. Ours is huge, over 43,000 Ruby files, over 1,000 database tables, over 12,000 routes, 200 or 300 devs, probably 250 or 300 devs working on it every single day. It continues to grow. With this comes some questions, right? Because while this model of giant Rails apps has served us well, it can't scale forever. At some point, we need to do something else to break that apart. And that brings up some really tough questions. How do we split the world's largest monolith? How does our monolith talk to new services? Not as obvious as it might seem. How do we make it multi-region? So if we have like our AWS regions, you know, we've got an instance of this whole application in Europe, in North America. They do need to communicate to each other. They need to share data with each other. How do we do that? How do you break out things like search and reporting, which are sometimes tough problems and the source of a lot of performance problems? Having reporting queries baked into your primary database or having search baked into your primary database, along with the problems of making sure all the data gets into all of these systems downstream in a consistent way so that all these different data stores match at the end of the day. So I work on the streaming platform team at Procore. This was basically what we came up, how we're building solutions to a lot of these problems. That's actually a picture of our platform. If you zoom in on the water, it's actually like little ones and zeros floating downstream. This is at the core of our distributed system strategy. It is basically the backbone of our service-to-service communication. Amongst other things, it's our way of replicating data zone to zone. It's a suite of tools built by my team and I that allow sort of self-service creation of services that can publish and consume from streams so that we can finally break this monolith, right, and start developing microservices. So streams themselves, right, they go by a few different names. You might hear it called an event bus, right, a transaction log. I made the icon a log, get it? Transaction log. Yeah, a stream. Some people call it a pub sub, right? For those of you born in the 90s, that is a newspaper. It's like the internet, but on paper. And at the heart of this, right, is Apache Kafka. Kafka is a distributed log, right? It was invented by Jay Krebs, who was at LinkedIn at the time, and it is fundamentally, I should say that Apache Kafka is not the only solution that does that. There are some competitors. Amazon has Kinesis, which is similar, but not as fully featured. Google has Cloud PubSub. I don't know who actually uses Google Cloud, but so there are competitors, but most people in this ecosystem are using Kafka. It's kind of the tool of choice, definitely the most common, and has the most tools and things built into it and libraries. So Kafka is fundamentally the system where you have something that publishes data to what's called a topic. A topic is like a single stream, so you publish to a Kafka topic, and then something else consumes from it. It is... So I'm going to go into just a few nuts and bolts about how you read and write to Kafka from Ruby before we get into the fun stuff. So there's this wonderful gem. It's called Ruby Kafka. It's maintained by the fine folks at Zendesk. If you're here and you work on this, I love you. Please come talk to me. And using it is actually pretty simple. You instantiate this Kafka client. You pass it some config options with broker names and things like that. You deliver a message. You've got the message. You've got which topic you're going to write to. And you've got a partition number, which I'm going to talk about in a second. So not too difficult, really, to kind of get started with this once you have Kafka up and running somewhere. It also has an asynchronous producer mode. So the first one I showed you was synchronous, where you actually write to Kafka, it blocks, you wait for a response, and then you get your thread back, right? There's also an async version of this, which when you publish a message to Kafka, actually puts the message in a in-memory background queue, and there's a background thread on your web servers that takes those messages in that queue in small batches and publishes them to Kafka. The nice thing there is that it doesn't block your request, right? So in your Rails app, users aren't waiting for you to publish to Kafka, and you return a little bit faster. The downside of that is it's not durable. So in like a kill 9 scenario, or if your server crashes, you can lose messages that way. All very important things to consider. In fact, I've got a whole section coming up about how to produce and how to produce consistently based on your needs. Kafka topics are broken up into partitions. So what happens is these consumers, they subscribe to a Kafka topic, they tick off one small batch at a time, and they process it, and then they grab the next batch. To make that scale, it's broken up into partitions based on a partition key. You choose your own partition key. That could be something like user ID, and for that particular partition, messages are in order. And then you can parallelize it by running consumers, right, up to one consumer per partition. That's how Kafka scales. When you're reading from Kafka, like just in basic Ruby, once again, this is the Ruby Kafka gem. You configure it with these broker names. Brokers are like the Kafka servers, right? You have got this loop here. You subscribe to a topic in this loop, and it just loops and loops and loops, consuming micro batches of messages. How you do exception handling in there is real critical if you don't want it to stop, and definitely something to pay attention to because it determines basically your ordering guarantees, which is something important I'm going to talk about a lot. If you're using Rails, right, you can in fact turn your Rails app into a Kafka consumer. It is a little bit fraught. It's not necessarily straightforward or easy, but if you basically make a new class, right, call application initialize that starts off all your autoloaders and your initializers, right, which that allows you to use like your model classes and things like that. Then you subscribe to Kafka and you start processing messages. So this is skipping the whole web server, right, and the normal Rails server. We're basically just running a Ruby file directly and then loading Rails classes. And you can do that. Depending on which version of Rails you're using, it may or may not be more complicated than that to get the environment to load. But that's nice. You can write all the classes you've already written in your Rails app if you don't want to break them out into a gem or something like that. So why Kafka? This is the author, Franz Kafka. He wrote a great book about a man who turned into a cockroach. Kafka has some interesting guarantees that aren't really true about most other similar but different technologies. One is at least once delivery. A Kafka consumer always retries until it succeeds in processing your message. So it will sit there, it's subscribed to one partition, it will read the messages off that partition, and if it fails to get an acknowledgement back, it will keep trying, and in that way, you are guaranteed to never lose a message, provided someday you fix your bug or your performance issue or whatever it is that is preventing that message from getting through. It will sit there and retry forever. It's a disk-based storage system. The messages don't get lost. All the messages are replicated on disk across brokers, and it's got a retention period, which I'm going to talk about. Kafka gives you guaranteed ordering. The order in which the messages go in is the order in which they are processed, and that is key to all of this. I can't overstate how important that is for these types of systems, because that is what allows you to make a consistent system. Say, for instance, you've got a Rails app, right? And it's writing to a database, and then you publish to Kafka. If you want that, and that downstream, you're consuming it and writing to another database, to a search index or something. What you don't want to do is have a record get inserted in your database and then updated again, but the last update goes before the first one, and then you overwrite new changes with old ones. That's bad, right? Because then your data is inconsistent. And that's why this guaranteed ordering is so important. It also multicasts. So you can have multiple consumers on a single topic. That's key too. This is what really allows your system to be really flexible. And you can replay it. Because Kafka messages are retained, often you set your own retention window. Ours is a week. If you mess something up, right, if you forget to write a column to your database, you can go back in time, reconsume the stream, and repopulate your database. So with at least once delivery and guaranteed ordering, we have a system that is consistent. With multicast, we have something that is democratized because many people can consume this, use cases you don't even know about yet, and it is decoupled. You have decoupled the upstream and downstream, and different services that are consuming are decoupled from each other. This is not necessarily true for similar things, right? If you're used to RabbitMQ, Amazon SQS, they don't have retention. You pick that message up off the queue, it's gone. You can't replay it. They are not ordered. So you can enqueue two things often, depends on some of the settings, but you can enqueue two things and have them, the order be swapped. You can have them processed at the same time. This is also true of Sidekick, which is different, but it uses Redis as a queue. Often you get parallel execution of these things, which is not consistent because it is not ordered, and you can have old things overriding new things if you're not careful. And if we're actually running Kafka, you've got some options. If you don't actually want to spin up your own Kafka servers, Amazon has a relatively new one called MSK, even though they have a competing Kinesis, go figure. Heroku's got a great one. Surprisingly, we used to use it. It's actually really awesome, and it's cheap, and it's fun. And then Confluent is the Kafka company. They make all the open source tooling, but then they've got commercial versions of this stuff, cloud-hosted versions. Use cases, that is Jay Krebs, the inventor of Kafka. He did not turn into a cockroach. So, simple question here. Actually, it's not that simple. It's deceivingly complicated. What is the best way to make one Rails app talk to another? All right, well, a simple thing to do would be an HTTP post. So, that's not as great as it sounds. It's not tolerant to errors. If that downstream system is offline, if it's being deployed, if it's bogged down due to database performance, that's going to return an error, right? And then you either have to swallow that message and lose it, or you have to return an error all the way back to the user. So it is not fault tolerant at all. If this is not your app downstream, if it's a third-party app, you're especially vulnerable here. This can create big problems. Latency is also a problem because you don't know 100% the performance characteristics of the downstream app. If the database is bogged down, you could be waiting for seconds for that thing to return. If under peak load or if someone runs some giant query that they're not supposed to run, you could be sitting there waiting forever. Your upstream one could actually time out. Whereas writing to Kafka is fast. Once you write to Kafka, it's fire and forget, continue on with your life, right? And the downstream system will catch up. And it's also one and done. There's no downstream consumers here. The history is kind of lost, unless you're logging all requests, right? The history is lost. You can't go back and examine your past history and things like that. It's one and done. Not so great. gRPC, this is like a streaming technology, Google streaming technology, which is a much more efficient protocol than HTTP, but it suffers from a lot of the same problems. Again, you can multicast with that, but again, it's not fault tolerant, et cetera, et cetera, et cetera. Kafka fixes these. It's buffered, which means it can smooth out performance spikes, right? Because if you get a spike of writes, the reads are relatively consistent. It's based on the number of consumers you have and the number of partitions. It's durable. The message is not lost. You can go back and replay. It's consistent. And it's democratized, meaning lots of consumers can subscribe to it, which can pay off in the future for use cases you haven't even anticipated yet. Item potency is key. I put that key emoji on there to reinforce it's key. That was my last-minute addition in the speaker lounge. It's key. Because Kafka always retries, there's always the possibility of duplicated messages. So you have to upsert on the right side there. Otherwise, you could get duplicate inserts, right? So it's got to be idempotent operations. Here's use case number 2. So use case number 1 was service to service. Use case number 2 here is this kind of multicast idea. Imagine you've got this service and a new user signs up. There's a lot of things you need to do. Send a welcome email. Insert a search record, like maybe in your Elasticsearch cluster, so that person is searchable in your directory. Maybe you suggest people to follow or recipes to try or whatever, and you've got some machine learning model or something that you're calling on. Here we've split that up with multiple consumers. Those are now independent. They're decoupled. You've got independent retry for each one of these. And because of guaranteed delivery, you know that even if one of these services is down, it doesn't affect the other ones. And the message will never get lost. As long as you get it running back at some point, your messages are still there. And you're guaranteed to get all these steps to complete. Heterogeneous data stores, similar but different, but this is a great case where you've got a Rails app. Primarily you're running on Postgres, but a lot of us also need other things. We want to sort of mature a bit and use a real search engine like Elasticsearch, right? Maybe you want to use a reporting database like Snowflake, which is great for running big aggregate queries. This allows you to make sure that all of these databases are consistent and have the same data in them. If your app writes to Kafka, you know that because of its guaranteed delivery that all of these will eventually get the message. And then you'll have the same thing in every database. And once again, that's where the ordering comes in. Not only will they get there, they'll arrive in order. So you don't have old things overriding new ones. One thing I do have to mention, because if you look at Kafka, you're going to come up with this. It's called Kafka Connect. And this is a solution to make it easier to produce and consume from Kafka. It's this application. You spin up a bunch of pods, right, like a bunch of containers of this. They talk to each other, and you can create consumers and producers just by submitting configuration files. So if you want to write to Elasticsearch, write to S3, HTTP post these batches, you just send these JSON configs to Kafka Connect, and it spins up producers for you. And in that way, a lot of the downstream stuff, like the typical things of like, take a message, write it to a database, take a message, HTTP post it somewhere, take a message, put it in S3, right? You don't have to write all that code. And like I said, this works really well on the consuming end. So you've got all these built-in database connectors, so you don't even have to develop this stuff yourself. What the heck? Now, it is Java, but, you don't actually have to write that much Java to use it, right? This is the Despair girl right here. She's really sad about that. And then use case number 4, right? Similar but different is this idea of a data lake. So if you're not familiar with like sort of enterprise data infrastructure parlance, a data lake is like just a giant catch-all of all your enterprise's data. Most people, including us, we implement this with S3 buckets, right? Amazon's cheap storage. And this is kind of cool. If your services are communicating each other in Kafka, there's no reason not to put an HTTP sync on every single Kafka topic and back it all up to the cloud, right? So it is there forever. We have ours there. We've never used it, but it's there in case we do, right? But seriously, there's new technologies are coming online that make like basically querying S3 buckets as if they're SQL cheaper and better, and it's been slow to mature, which has been frustrating, but this stuff is coming, which basically can make all like years and years and years of your enterprise's data searchable and queryable, which is really powerful. And Kafka Connect helps you get it in there. I tried to put like a lake emoji or like a lake clip art behind the buckets, but I couldn't get it to look good, so I just used a blue circle, because lakes are usually kind of ovular and less square, and I made it blue to look like water. My dream, ultimately, we have not built this, but I would love to, would be the ability to take historical data out of our data lake and load it back into Kafka. So if you wanted to say, hey, I want to reprocess all of 2021's data to power a new machine learning model, we could press a button and have this tool created that goes, whoosh, puts it in Kafka, populates this thing. Or if you wanted to say like, hey, I've redesigned my reporting database. I want to use a totally different table structure. Drop the old database, replay traffic from the beginning of time, repopulate it that. We're trying to build a system where for every domain, like a domain is like a tool or a slice of functionality in our system, right? That we have complete historical data and the ability to rebuild it, to basically repopulate by replaying all the traffic. We don't have that yet, but we're going to get there. I forgot to change the title slide. But finally, use case number 6, this should be titled Event Sourcing. We all know that in a Rails project, right, you typically attach it to a database, right? But you don't necessarily have to do that. If you read a lot of the literature on Kafka, they advocate this pattern where the Rails app or your producing app writes to Kafka first. Then you have a consumer that writes to database, and all the app does is select from the database. So it reads, but does not write to the database. This decoupling is really powerful because, again, if you've got multiple databases, a search index, right, a machine learning model, a reporting database, and things like that, it's easier to make sure they're all the same. We call this event sourcing. That's, definitions may vary on what exactly that means. But it's a powerful thing. And if you're doing this in Rails, of course, then you get to go and reorganize your Rails app. Rails is great for this, the way you can customize it. You'd have different read models, different write models, right? And you get to basically redo your whole data layer and create your own framework, which would be fun. And interestingly, when you do this kind of thing, usually this is, not usually, but often, I'd say usually, this is coupled with materialized views. So imagine your basic widget, right? You've got a widget list view that lists all the widget. You've got an item view that shows the details of that widget. You've got an aggregate view, how many of those widgets sold, day by day, month by month, week by week. Using this, allows you to pre-materialize those things, to pre-compute them, to make these tables with that data in it so you don't have to query your database and calculate that on the fly, right? There are many ways you can do it. Postgres has materialized views. You could use a NoSQL style store, which is pretty common, right? And actually basically create data that matches what your page looked like. So list view in this table, an item view in this table, right? An aggregate view in this table. You need Kafka to do that because it's the only way to ensure that they all get the same data. Because of guaranteed delivery, 3 consumers, right, really consumer groups, 3 consumer groups writing to 3, you know that they all succeed and you don't get those inconsistencies again. If you try to just insert into list view, insert into item view, insert into aggregate view, if something fails, right, then you're inconsistent and you've got bad data forever, basically. And then once again, right, with this event sourcing pattern where you don't write to your database, it does make it easier for heterogeneous stores, right, a reporting database, a search index, et cetera. There's a name for this, right? This is one version of a pattern called command query responsibility segregation, right, which basically means that your read model is different from your write model. And it already kind of is. If I were going to take a shot at Rails, you've got this model class, which represents a table, right? Let's say that's a user. You always write one user record at a time. But when you read, you're often inner joining, aren't you? Join, join, joins. And how many people have Rails apps where like half the queries are like 8 joins or more, right? We do. So fundamentally, that is a different shape of data, isn't it? It looks totally different, yet they're one model file, which leads to some confusion. This definitely smashes that the extreme way by totally different tables, right? Use case number 6, region-to-region replication. We have customers in America, we have customers in Europe and Australia and Canada and other places. And we do need to actually share records because we have general construction contractors who hire in Europe, who hire subcontractors in the US. And Kafka makes a great way to basically replicate that across regions by having one consumer. There are a number of patterns you can do this with. You can have one consumer post to another region. There's this thing called Mirror Maker, which replicates a Kafka topic conveniently. It is part of Kafka Connect. So once again, if you don't mind a little bit of Java, right? You can employ that, right, and replicate topics across zones. One more pattern that I will mention is that, like I said, turning your Rails app into a Kafka consumer, it definitely can be done. There's another way, which is to have an HTTP sync, which is just something that consumes a microbatch from Kafka and HTTP posts it to your service, right? You still get the same retry mechanisms, because if the post returns anything but a 200 response, it continues to retry. And that saves you some of the ops headaches from having to spin up every other instances of your Rails app, right? Or kind of hack the Ruby bootloading, the boot framework and stuff like that to figure out how to get your classes to run that way. The other thing you could do is just use a plain old Ruby consumer, right, and take your model classes out of your Rails app and put them in a gem that you share. So let's talk a little bit about getting stuff into Kafka, because if you don't get it into Kafka the right way, if you can't make your message production consistent, your whole system's going to be inconsistent. Inconsistency is bad. Imagine you've got someone's medical records or dealing with someone's money. God forbid, you'd have one database that shows have X dollars or, X whatever maladies, and the other says something else. You wouldn't want that. There's an issue here that I've sort of glossed over, but I'm going to address it now. Rails apps have a database, typically. And you may also want to write to Kafka, right? For downstream things, so other things can see this data, this message. This introduces a problem called dual write. What dual write means is, all right, imagine I publish to Kafka, and I open a database transaction and insert into my local database, right? Well, you've published to Kafka, but your database transaction can fail. It can roll back, and now you got something in Kafka that's not in the database, and you are inconsistent. If I put it at the end, that doesn't help, right? Because you put in the database, and then you can fail to publish to Kafka, right? Now you are inconsistent again because your local database does not reflect what's downstream. It doesn't help if you try to put the publish in the middle of your database transaction, which is typically a bad idea anyway. But sadly, we do it a lot. Side note, right? Quick side note. If you are using Sidekick, right, you may already be victim to this problem and not even know it. Sidekick uses Redis, right? Sidekick or Rescue, these are these Ruby job processing frameworks. If you are inserting into a database and then queuing a Sidekick job, there's no guarantee that you get one or the other. And that is also a source of inconsistencies. Or if you're using Postgres for your database and Elasticsearch for search, right, there's no guarantee that you get one or the other because you can always fail in the middle. So to fix this, we have a system called change data capture. And this is a key to our, like I told you, we have this giant monolith and we're trying to split it apart. This is going to be a multi-year effort, and it's probably going to take us 8 years and take hundreds of developers. But this is one way we get the data out in a way that avoids that dual write, which is change data capture. We use this system called Debezium. Conveniently, it is a Kafka connect, right? Source connector, which means that to customize it, we have to write Java. But what it does is it actually reads the Postgres write-ahead log, right, which is right where the data gets serialized on a disk in a single process, reads it, writes it to Kafka, and in that way you can actually just track a table. You give it the name of a table. Say it's my users table, and it will read the data as it is written to the write-ahead log in Postgres and publish it to Kafka. And in that way, your database always matches what's in Kafka, and you've fixed the dual write. Java, oh my gosh. One more quick thing to realize about that is it comes with some caveats. A Rails database is typically, if you're using, like Postgres, a relational database, it's typically a normalized database. Something simple like a user record, a product record is often split into multiple tables. You are leaking the implementation details of that downstream if you're just doing direct change data capture. Right? We all know these wonderful Rails patterns like single table inheritance and polymorphic relationships. Now, guess what? You're dealing with that downstream, right? Which is not very fun. So the way around that is using this pattern called transactional outbox. It works like this. You insert, like, say this is a denormalized user, or a normalized user record, right? So you maybe insert into users, you insert into accounts, you insert into profiles. Then you do a fourth insert into a special table called outbox. Right, which could contain all that stuff, right? You could take all the things that went in those 3 tables, GM it together, maybe even in some JSON blob, right? And then publish it to the outbox, and then you use change data capture to follow the Postgres while log, right? Consume that table, publish it to Kafka, and in that way, because this is all in a database transaction, see, begin, commit, either all of them succeed or all of them fail, and you're not left inconsistent. Running Debezium, right, is it's actually not that hard. You turn on Postgres logical replication. You do have to run Kafka Connect. We've got it in Kubernetes. Then you submit this configuration file and with your database connection strings and stuff like that, and it kind of attaches and reads all the changes. We used to be, I don't know if it's still true, the world's highest volume Aurora Postgres instance in AWS. We were processing something like, we still are, processing like something over 200,000 transactions a second. And it keeps up on a single thread. You must choose, but choose wisely. It had this RailsConf, right? I had to put a meme somewhere. So we've got a few methods of publishing. Direct to Kafka synchronously, which is the safe way to do it. Asynchronously, which is faster, but you might lose messages if the server restarts, right, or crashes. CDC, just tracking your database tables and publish them to, that's change data capture, publishing them directly to Kafka. Or transactional outbox, the cleaner way to do it because you can decouple your stream from your database. Consistent streams require consistent producers. Your requirements may vary. Honestly, a lot of you could probably deal with the dual write because, unless you're dealing with someone's medical history, it might not be that big of a problem. Don't overbuild it. Don't use this stuff just because we use it. We have different requirements than you. So, summing up a little bit of this stuff, streaming gives us a globally distributed, eventually consistent, near real-time way to send messages between services and across zones or regions in a way that is fast and reliable with strong guarantees that it is correct. Running out of time, so I'm going to go through this real fast. What's in a message? You've got headers, partition key, the data, and you got to choose a format, right? at your company, choose standard headers for all your messages, for all your different services. That allows you to route and filter and do different things. JSON is good, but you might consider a serialized binary format like Avro or Protobuf. It's more efficient, and these have schemas that get recorded in the schema registry and allows you to track schemas that vary over time. There's an issue if you're dealing with like data lakes and reporting databases of schema evolution. This helps you keep track of what message had what schema at one time. The future. One more thing, Apache Flink. I've got 1 minute. I don't know why they chose a squirrel for their, like, whatever. I guess those are cute. I find them annoying. Maybe they're annoying because they're cute. Because, like, you want to pet them, but no one's ever petted a squirrel, right? Flink is this thing. We're going to add it in the future. It's super powerful. I'm really excited. It allows you to join streams together, like crossing the streams in Ghostbusters, right? Imagine you've got a situation where you've got like a record of like a post, like social media, like a Facebook post, right? It has a user ID. Oh, well, wait. Now I've got another stream, like a Kafka topic with all my users in it. I can actually join them together. It's just like a SQL join on a stream. That's great. Imagine you want to make these searchable, right? Like in Elasticsearch, you can't index this post in your Elasticsearch if you don't have the name of the author in it, right? So by enriching stream, take one stream and enriching it with another, incredible, powerful stuff. You can aggregate records. Flink has a built-in data store, so you can aggregate it. My time is up. Aggregate records, right? Just like a group by, but on a stream. Great article, the original by Jay Krebs. Kind of talks in abstract terms about streams and about Kafka. This is essential reading if you get into this. I'm Brad Urani. I used to tweet. I don't tweet anymore. I quit. I was addicted. It made my life better. Except then I took that like compulsive scrolling and I got addicted to eBay instead and started collecting watches, and now I own 100 watches. Anyway, I work in Austin, Texas at Procore. We are hiring. We're a great place to work. Come talk to me. Unfortunately, I don't have time for questions, but you can come up and ask me if you want. Yep.